Hey guys, so I figured I would make a video that goes over the most missed questions. I know that we practiced some of these in class and got through as many as we could, but just to give you one more resource, we would walk through each question and try and go as deep as we can and explain each question. Of course, feel free to skip to what you need. By no means do I expect you to listen to every single thing. So, this was one of the most missed questions by far, and that's actually the order of this. So as we go, it's the less and less missed questions. But number 14, so it asks us to identify the vertex. So immediately we see that it wants us to find the vertex, and we should be thinking, okay, how can I find the vertex? And maybe one of the first things that crosses your mind is, well, I know if I had something like this, then it would be pretty easy to see what the vertex is. Because I remember that I can just read the inside, and I can just read the outside, and it would be opposite inside, so -2, and then the same outside, -3, and that would tell me my vertex. And if you remember that, you should also remember that that is called vertex form. And that's part of why we call it vertex form, is because it's so easy to get the vertex from it. Now, as you see, this doesn't quite match that format. Notice the square is just on the x, and here there's a square on x plus something else in it. Not to mention, there's this other single x term with a power of 1, and this one doesn't have anything like that. So this is definitely not vertex form, and we want to be pretty quick to identify that this is actually standard form. Now, when we're working with standard form, there's one of two ways we can find the vertex. We can first find the x-intercepts, and then use the x-intercepts to find the vertex, or we can also go straight for the vertex with an equation that we have for standard form. So, for standard form equations, and I'll go ahead and write it down here. So, for standard form equations, we can find the vertex with this equation. X is equal to -b over 2a. Now, what are a and b? Well, those relate to the standard form. And I'll actually go ahead over here, I'll write standard form so you can see what standard form is going to look like, and you can associate the variables. So standard form is going to look like this, and our a is in front of our x squared, our b is in front of our x, and our c is the non-x term. So we would need a and b in order to use this equation. Now, one more thing about this equation is you notice it says x, right? So that means that we're going to find a x out of here, which might sound kind of weird because I just told you that it would find the vertex. But we need to remember that a vertex consists of 2 points. A vertex is always going to have an x, and it's always going to have a y. So you want to ask yourself, does this equation get us the entire vertex? Right? And you can pretty quickly answer that, and the answer is no, it doesn't. It actually only gets us half the vertex. So this equation can conquer half the battle, which is good, and we can use other methods to then get the y, but realize this isn't the only thing to the question. So we're going to use this equation to go ahead and find the x value of the vertex. And now I'm just going to associate my variables a and b with my equation that is in standard form. So a would be 12, b would be 24. So I'll have -24 over 2 times 12. And now I just want to follow PEMDAS and calculate this and see what it equals. So this is -24 over 24, which is equal to -1. So I see that x is equal to -1. And because I'm on a tablet, I'll go ahead and be a little bit fancy. I'm going to erase that part and fill in my x because I just found it out. Okay, so I just found out my x value, And now I'm still wondering, what is my y value? So we have to go ahead and find the y value. And how you can find a y value is by using an x value to get to it. X and y relate, so if you have an x value, you can always find a y value that relates to it. How do you do that? Well, you're going to use your equation, and you're just going to plug in your x value. So notice I start off with my equation right here. And then I want to use that x value to find out what the y value is. My x can take me to my y, figuratively speaking. So I'm going to go ahead, and everywhere I see an x, I'm going to plug in -1. So I'll put a -1 right there. And I put parentheses around it because I don't want to forget the square is on the entire -1. I'm also going to put parentheses around this because I don't want to forget that, well, I don't want to mistake that for subtraction. So now I can start to calculate this, and calculating it, I still just want to follow PEMDAS. So I can do my -1 squared times 12, which is 12. 24 times -1 is -24, and then plus 9. I go ahead and do that addition, and it's going to be -12 plus 9. And then -12 plus 9 is going to be -3. So I see that my answer would be a vertex of -1 and then a y value of 3, of -3. Okay, so that would actually make this, I would select that one for my answer. Everyone's tests are different, so you want to make sure you find the answer that matches yours. Now, let's say that you couldn't quite get through this whole process, and you were, you were trying to maybe use the answers to figure out which one was correct. Or you could only get the -1, right? If you could only get the -1, you could immediately start to eliminate A, B, and D. And at that point, you would only have to prove that C doesn't work if you were going to select none of these. Now, this isn't a method available to us at the moment, but once we get a graphing utility, you can also graph this on a graphing calculator and then try and find out approximately where the vertex would be. But of course, we want these fundamental skills, and so before I let you cheat, like that, I want you to have these basic skills. Alright, number 18. So now we need to identify the x-intercepts of each. And kind of like we talked about in class, you want to have this general understanding about an x-intercept. Right? We make a statement about an x-intercept, which is the y value of it is always equal to 0. So we say an x-intercept always has y equal to 0. But you need to understand why that is. And really the key to being good at math is always asking, why do things happen? And finding out why those things happen. So we're going to look at this, and I'm going to make some x-intercepts for you. That's an x-intercept, that's an x-intercept. They all lie on the x-axis. And now you want to ask yourself, how far up and down did each of these go? All right, this one went up 0, so y is equal to 0. This one went up 0, so y is equal to 0. And this one went up 0, so y is equal to 0. So we can quickly conclude, unless you want to run more tests, which you totally could, but you would quickly conclude that every x-intercept is always going to have y equal to 0. And because we conclude that, that's a starting off place for our question. And that's a piece of knowledge that we could use to get this question going. So I'm going to go ahead and say that 0 is equal to x plus 3 squared minus 9. All I did was I just substituted 0 for y because I know I'm looking for an x-intercept, which implies that y is equal to 0. Right? We could really even just cross this off and be like y equals 0. Right? Identify the y equals 0 of each. Right? Like, what's the other variable when y is equal to 0? So now we have an equation, we have a missing variable, which is x, and we need to solve it. So we're going to use our algebra skills to start solving this. I'm going to get rid of the -9 on both sides by adding 9. And that's going to give me 9 which equals x plus 3 squared. Now I'm going to go ahead and get rid of the square by doing the opposite of the square. And you want to be able to answer this question, what's the opposite of a square? Okay, you need to know that that is a square root. It undoes a square. They are opposites. It's like a plus and a minus. So I do the square root on both sides. Now, one thing you want to know to do is you always want to write a plus and minus in front of the square root whenever you take it solving an equation. Now, the reason for this is because there could have been a negative hiding underneath the square that got lost when we squared something. Because if you notice, anything squared is always going to equal a positive. And the thing is, with 1 and 4, we could have easily guessed that, well, that was just 1 squared, and that equaled 1. Or that this was just 2 squared, and that could have equaled 4. So we never know if there was a negative originally in it, so when we're working backwards, we have to account for that by writing plus and minus. So I'll go ahead and keep on solving it over here. So now I'm just going to rewrite my plus and minus. I don't change that part of the equation. And I see square root of 9, and I ask myself, can I simplify that? Well, square root of 9, that's pretty simple. I can write that as 3. And then equal to, and now I have the square root of a square. Remember, square root and a square, how do they relate? Those are opposites. So they're going to cancel each other out, and we're going to have x plus 3 left over. So we get to here, x is almost alone, x is almost isolated. We can say exactly what it's going to be. And so we got to do one last step, which is subtract 3. So we subtract 3 from both sides, and this is where it may seem kind of weird to you. We're not going to quite combine those numbers yet. And the reason why is because the plus and minus represent two numbers. So we're just going to write them side by side. Plus and minus 3, minus 3. Now, why did I do that? That's because this secretly represents two equations, or two calculations. One of which is plus 3 minus 3, or positive 3 minus 3, and negative 3 minus 3. When we write plus and minus, it's saying that we have both of those numbers there. So we actually have to calculate two things. So we calculate those, and we can see that x is then equal to 0 for this one, and then x is equal to negative 6 for this one. Alright, and just like that, we got out an x value. We were given a y, which was y equals 0, kind of in disguise as the x-intercept. And then we plugged it into our equation, and we could find the one missing variable, which turned out to be x equals 0 and x equals negative 6. So that means our x-intercept should be 0 and negative 6, and so we can look at our answers and find out where we see that. Is it 5, negative 7? Well, no, obviously not. Is it 11 and 9? No, obviously not. X-intercept, are there none? Now, this is kind of an interesting question. I think a lot of you guys misread this. So for the x-intercept none, that doesn't mean none of these. That's not the same as none of these. What that means is that there's no x-intercept, meaning that you got out a number that is not real, or you had to take the square root of a negative number, which is something that we cannot do. So that's what that would mean, and I definitely got out 0 and negative 6, which those are real numbers, so there definitely is an x-intercept. Then I have negative 9 minus the square root of 3, and that's not bad, and you'll see sometimes we have answers like that. Like, that's not that crazy of an answer, but it's definitely not 0 and it's definitely not negative 6, so I'll cross that out. So that leaves none of these, because I've eliminated all my answer choices. Now, another way that you could approach this problem is more backwards and using your answers to check your equation. And what I mean by that is you can plug in your numbers and see if it gives you an x-intercept, right? So how would I know if I plugged in something that gave me an x-intercept? Well, remember, x-intercepts always have y is equal to 0. So if I plug in one of those numbers from here and I get y is equal to 0, well then that tells me that's an x-intercept. So let me start off and I'll practice plugging in a, right? And I'll pick -5 to plug in. So I have y is equal to -5 plus 3 squared minus 9. So now I have to calculate this. And so I have -5 plus 3, which is -2 squared minus 9. -2 squared is going to be 4 minus 9. 4 minus 9 is going to be equal to -5. So I see that plugging in -5 gave me y is equal to -5. Does that agree with y equals 0? Well, of course not, right? We just found that y is equal to -5, so these two are incompatible. They're not the same. So therefore, a is definitely not an x-intercept. And that's a method that you could use with every single one of those. Now, I don't want to show that here, but understand you could go through with each one of these, plug them in, and see if it makes y equal to 0. Okay. Alright, so axis of symmetry. Now, like we talked about, axis of symmetry is always going to have a very, I guess, special relationship with the vertex. So I'm sketching a parabola so we can think about an axis of symmetry. And I put my parabola so that way the axis of symmetry is right here. And actually, let's kind of move it off of there so it'd be a little bit easier to see. So when we have a parabola, let's say it looks something kind of like that, we could see our axis of symmetry would be somewhere right there. It would look something like that, because it would perfectly divide our parabola into two. Now you realize that we also have a vertex, which is right in the center of the parabola. Right? You see the relationship, I'm sure you do. The vertex is going to be right where the axis of symmetry is. So remember, our vertex is going to have an x and a y value. So then, how does our axis of symmetry relate to our vertex? Well, the axis of symmetry went over this far. It scooted to the right by that far, or it scooted to the right by a value of x, meaning the same as the x value of the vertex. And that's why we conclude that the axis of symmetry is the same, right? All of this just means the x value of the vertex. That's how we can find the axis of symmetry, because no matter what, our vertex is going to scoot over, and our axis of symmetry is going to scoot over with it and be up and down in that direction, that distance away from the origin. So if we just find the x value of the vertex, we can then find our axis of symmetry. So really, this isn't even a axis of symmetry problem as much as it is a vertex problem, because we just want to find the x value of the vertex. So okay, so now I look at my equation and I recognize that this is in standard form. And so when I recognize that this is in standard form, some really big light bulbs are going off my head, right? Because I remember that we have an equation to find the x value of the vertex for standard form. And that equation is x is equal to -b over 2a. Right? My standard form is ax squared plus bx plus c, and I can see what a would be, I can see what b would be, and I just plug them in to this equation. So I'll go ahead and I'll start plugging these in. I'm going to see that b would be 2 because it's right next to the x, so b would be 2. So -2. And I put parentheses around it, but you don't have to. And 2. And a, now I don't see a number in front of here, but I see a negative. So what number represents a negative? Well, it's just -1. Okay, so I calculate this and I have -2 over -2, which is equal to 1. Okay, so the x value of our vertex is 1. Now, if we were looking for the entire vertex, remember, a vertex consists of x and y. But notice the axis of symmetry is just the x value of the vertex. So we don't have to keep going past here. This would actually be our axis of symmetry. And so I'm going to look over here for 1, and I actually see two answers, right? I see a y equals 1, and I see an x equals 1. And this is where you need to be clever, and this is where you need to remember that the axis of symmetry is the x value, not the y value. If it were the y value, it would look something like this, right? That would be the y value. But that wouldn't make sense in terms of a symmetrical line. So that's not our axis of symmetry, it's just the x value. Whoops. So that would mean our answer is E. So I'm just going to erase that. Right, that was a hypothetical that we considered. And we see how that doesn't make sense, right? And that's kind of what a lot of math is about too, is like considering what if this was the case, and then proving how, well, that couldn't be the case because it makes other falsehoods. So we see that E is going to be the answer there because x is equal to 1. We found it just like that. As far as what I need to know for that, I needed to know my equation that told me the x value of a vertex in standard form. Okay, so this was another very commonly missed one, and I was kind of surprised by this, but I think you guys might have just gotten a little bit confused on your rules. So when we look at this, we're going to see an absolute value equation. So we can know that the parent function of this is going to look something like this. Right? And actually just the pure absolute value function is going to look like this when it's graphed at the origin. Right? Where that would be y and this would be x. So now we don't have a pure absolute value function. We have something that's x plus 2 with the absolute value bars around it. So there's a plus 2 that's happening, and it's not happening outside of the absolute value bars, it's happening inside of it. And so this is kind of what we could call vertex form, because what's happening on the inside is going to determine where it's shifted left and right. And it's going to do so in the opposite direction, or in a offsetting direction. So when I see the plus 2 on the inside, that means it's going to move in the opposite direction, negative 2. Right? So instead of moving to the right 2, it's actually going to move left 2. So I'm going to look for one of these guys that's been shifted left 2. Which one would it be? Well, I see that this one has been shifted left 2, and it would be right there. So what do you need to know for this? You need to know how to read your equations. And you need to know how to find out where the vertex is going to be pretty quickly. Now, another technique that you could use for this is you could make a table. And this is a technique that's very tried and true. It will always work, and you can always do things like this. So I could make a table here, and I could just start to plug in numbers. So I can pick -1, 0, and 1. Just picking some random numbers. So -1 plus 2, that would be +1. The absolute value of +1 would just be 1. So I plugged that -1 into the equation to find out what y would be. So now I can also do x. I plug in 0 into there. 0 plus 2 is going to be +2. With the absolute value bars, it still just stays positive, so that would be +2. Then I can plug in 1 into there. 1 plus 2 is 3. Absolute value of 3 is still just 3. So now I can start to look for an equation with these coordinates. And even more specifically, intercepts are typically easy to find, and I see that has an intercept at 0, 2, or 0 on the x-axis and up 2. So I could look for an equation that has a coordinate over 0, up 2. And so I look at this one, over 0, up 2. Well, no, that one fails. That doesn't work. Over 0, up 2. Well, that works, so this one could be a possibility. And this one, over 0, up 2. Well, that one works too, so it could be a possibility. So then I could start to check other points. So over 1, up 3. Over 1, up 3. Well, no, this one fails. That doesn't work. Over 1, up 3. Well, no, this one fails too, and it doesn't work. And so that leaves me with an option of either none of these or this one. And so if I can prove that this one doesn't work, that's pretty easy, because then it's none of these. However, I'm going to plot over 1 up 3, and I actually see that that falls perfectly on the line. And so at that point, even if I couldn't tell for certain where the graph was moved to, I would make a pretty strong guess that this is my correct answer. All right. So for this equation, oh, and I'm sorry, I actually didn't put the instructions in here. So the instructions of this are to find the x-intercepts. Okay, so you need to find the x-intercepts of this equation, and right now we only know one method of doing it, and the method that we know to do this is by factoring. So when we have a standard form equation, the thing is we can't just plug in 0 for y and start to solve it. And actually, sorry, let me back up. So when we're looking for the x-intercepts, remember, our x-intercept is just code for y equals 0. Y always equals 0 when we have an x-intercept, so we're just going to plug in 0 to that equation. So then we get to 0 equals x squared minus 2x minus 35. And now, a lot of us may have the intuition of trying to solve this, and that's not a bad intuition, that's very good to have, and you may start adding 35, and now you get 35 is equal to x squared minus 2x, and you get to here, and, well, you might not know what to do, or maybe now you're scratching your head, and you're kind of scrambling. And the thing is, you're doing that for a very good reason. The reason's because we can't solve this any further. There's an x squared and there's an x. We know that these are different terms, and so they can never combine. So we're going to have x in two places, so it can never be isolated like this. We can never find out exactly what x equals. So we have to take a more unconventional approach to solving this. And that's where factoring comes in. So we can go ahead and factor this. And then see if we can maybe do something with it. So factoring, remember, we're always trying to find a times c that adds to b. A times c is 1 times negative 35. And b is going to be equal to negative 2. So what numbers multiply to negative 35 but add to negative 2? Well, that would be 5 and negative 7. So those are my two numbers that fit this equation perfectly, that fit this trinomial perfectly. And so I'm going to use these to then factor my equation. Now a is equal to 1, so I can take the shortcut and I can just say x plus 5 and x minus 7, just like that. Okay, and so I factor it, and now I can reconsider this equation and think if this is any easier to solve. And it turns out it actually is. The reason why is because I'm looking for two things that multiply to 0, aka I just need one of these to go to 0. So I can rewrite this as 0 is equal to x plus 5. And I can also rewrite this as 0 is equal to x minus 7. Now why can I do that? You can think of it like just one of these needs to go to 0 in order to multiply to 0. Or you can also think that you divided by x minus 7 on both sides to go there. So you cancel those out. 0 divided by x minus 7 would still be 0. Or you can think of dividing x plus 5 by x plus 5. Those would cancel, and then you'd be left with x minus 7 and still 0 on that side. Either way, you can write those equations, and you'll find that this will give you a solution that works for this. So we solve these, and we can kind of see that this will be x is equal to 7. Let me rewrite that. It's a little bit messy. X can be equal to positive 7 because we would have to add 7 to both sides. And we would also see that x can be equal to negative 5. Alright, so just like that, we found our x-intercepts. We can now go ahead and look for this in our answer, and I do see that this looks like an option with our x-intercepts. Now, a way of solving this problem backwards, especially when we have multiple choice, is we can plug in some of these numbers and see if these numbers are going to generate 0 for y. Because remember, an x-intercept is always going to have y is equal to 0. So let's take, for example, b, right? I could plug in y is equal to 5 squared minus 2 times 5 minus 35. And I can calculate this and see what it equals. That'll be 25 minus 10 minus 35. 25 minus 35 is going to be negative 10. So negative 10 minus 10. And then this will be equal to negative 20. Sorry, I guess I just realized I did a trick. So I saw 25 minus 35, and I knew that'd be a little bit easier to calculate. I guess we could always go back and do it a different way. That might have been a kind of like a big trick. So let's go ahead and do that a more formal way or more basic way. So 25 minus 10 could also be written as positive 15 minus 35. And 15 and minus 35, or 15 and like a negative 35, could be a negative 20, which is still the same answer. So notice, right, when I plugged in 5, I got out y is equal to negative 20. And I know that an x-intercept has to have, an x-intercept has to have y is equal to 0, so this could definitely not be the answer. Okay, so that's how you could go through this, and you could ultimately use your answers to check if that's an x-intercept. All right, so we have another axis of symmetry problem. So remember, the axis of symmetry is going to be the same thing as our x value of the vertex. So really this thing is just axing for the axis of symmetry for the x value. Or yeah, the x value of the vertex. So we can treat this just like we're just trying to find the x value of the vertex. And now I look at this and I see that this is actually in vertex form. Now, that's actually kind of good because vertex form is a little bit easier to find out what the vertex is. Remember, we're going to have our rules for looking what's happening inside the operation or inside the parentheses and what's happening outside. Remember, inside is left and right and it's the opposite, or it's a offset. And outside, it is up and down and it is not an offset. It's the same thing. So this would be negative 3 that's going inside. So negative 3 left, and then 7, which would be up. So our vertex would be negative 3, comma 7. And so remember, the x value of the vertex is just the axis of symmetry, so this would be our axis of symmetry. So which one is it? Well, I know it's not going to have a y with it. I know it's not going to have a y, and so it needs to be this one. Okay, this was kind of a tricky one, but this takes a little bit of an understanding of relativity, because the idea behind this is that you have to find out what happened to the function. Now, it says this is what the function was originally. So what's the significance of that, or why does it matter? It means that we're not starting at our normal numbers, aka we don't look at this and say that this was stretched by 8. Because it didn't start at 1. If this started at 1, we would say that this was stretched by 8. However, that's not the case here. This was stretched by 4. And the reason why is because it started off at 2, so we need to ask ourselves, what did I need to multiply it by to get to 8? Right? We notice this is multiplying the function, so we need to ask, what does this need to multiply by to get to 8? So that would be 4. So we can anticipate a stretch of 4. Okay, so that's good. And now I also notice that this started off positive and it turned negative. So that means I also had to multiply it by a negative somewhere. And I should know that multiplying by a negative is going to flip things vertically. Okay, so I still have these three answers which are in the run-in to be correct. Now, I also see a -5 out here, and this might be one of the easiest to calculate. And I notice that there's actually nothing outside that we're starting with, meaning that we have a -5 here, but it started from 0, or the original number that we're used to. So it's going to start from 0 and go to -5, so that's going to be an offset down of 5. So we're going to go down 5 and down 5. Cool. So we still got two answers that could be correct. Now our only question is between whether it went right 4 or left 4. Now this is where we need to think kind of critically about it, and we see that this one started off at +2 and it went to -2. So our question would be, what do we need to do to +2 to get it to become -2? Right? So what do we have to do to that? Well, we have to take away 4. And if we take away 4 from 2, it would then become -2. So what happened inside of there? We had a -4 inside, or we took away 4 to get to our new place. So we took away something that was on the inside. So we're going to have a -4, and this is where we now have to remember what our rules are. Remember, the rules are on the inside it goes left and right, and it goes in the opposite of what we expect, right? Or the opposite direction. It is what we call an offset. So if I have -4 inside, it doesn't go 4 to the left. It's actually going to go the opposite direction and go 4 to the right. So I see just right there, this is going to be my final answer. Not those guys. Okay. All right, so you have to sketch a graph of each function. And now we do have the benefit of this being a multiple choice, so we don't have to sketch a graph. We just have to find the one that looks right, or the one that's going to have some points that make sense. So we're going to look at these, and immediately I notice the relationship between my answers and my equation, and I notice this has a cube root in it. And I should know that the cube root is always going to look something kind of like a curvy S. Let me draw a better graph for you. This is what the parent function of a cube root will look like. So cube roots will normally have this kind of S-like shape to them. And this is something we want to become familiar with because we're going to see them a lot. Right? Cube roots are normally going to have this kind of shape to them. So immediately I can see some of them have that shape, but this one over here doesn't. It stops right there. It doesn't go like this. So this one is going to be a big no, because it doesn't even match the shape of a cubic. And that's actually, if you know, the shape of a square root. That's a square root function graph. All right, so now so far we have 3 other contenders. They could be correct. We don't quite know. And we can also look at this and we can remember our translation rules, or the rules that move these equations around. So I have +1 and I have -2. Notice +1 is on the inside, so that would be going left 1. And -2 is on the outside, so this would be going down 2. So I want to look for something that has that center point of my graph that's been shifted left 1 and down 2. So I'm looking on here, I want to find something that has a vertex that went left 2 and down 1. So couldn't be that one because left 2, oh, whoops. I totally mixed that up. My apologies, guys. I was saying left 2, down 1. It's actually left 1, down 2. So left 2, down 1. Oh, I think I just did it again. Sorry, I'm preoccupied. There you go. Okay, so left 1, down 2 would be right there and right there, and that actually looks like a vertex. That's actually a pretty convincing vertex. So I'm already pretty suspicious that this one is going to be my correct answer. But let me go on and check the other ones. So left 1, down 2, I'm going to look for a vertex there. So left 1, down 2, and that point would be there. It doesn't look like it quite gets on the graph, but maybe it could be. But again, that should be my vertex. Right? That's my vertex right there. And this is also going to be my vertex. So I should expect to see that kind of curvy point, or that curvy point right there, which isn't happening, so that's definitely not my vertex. All right, and so now I go over here and I can look at this one. Again, going left 1 and down 2, that point would be there, and I see that point isn't even on this graph. So I can immediately know that this graph is just not going to work. So far, I've eliminated all those. I just haven't quite verified that this one is my correct answer. Now, what's another way that you could verify this is your correct answer? Well, you could plug in some other numbers to here. So I could make a table, and I could plug in, let's say 0. And so calculating that would be the cube root of 0 plus 1 minus 2. When I calculate that, that would be the cube root of 1 is just 1. So that would simplify to 1. And then the cube root of 1 would just be 1. Right? So I could think of that as being just 1. And then 1 minus 2, well, that would be a negative 1. Whoop. So yeah, that would be a negative 1. So my coordinates would be over 0 and down 1. So I could go over 0 and down 1, and that should be a point on my graph. Over 0, down 1, and yes, that is a point. So basically I'm just verifying that this over here could be a coordinate on this graph. Okay? So it points to that. The biggest thing is that the vertex is right there, so we can know that that is the vertex. All right. Okay, so another one. So we have to sketch another graph, and again, it's multiple choice, so we have the benefit of not having to sketch the graph, but we do want to find some key features of it to make sure we understand where it should be. So I look at this, and kind of like before, I can see that this is left 1 and down 2, and I can see that this is actually going to be left 6, and this is going to be down 4. I know my directions with that. I know that's what they associate to. So I'm going to expect a vertex at left 6 and down 4. So I'm going to go left 6 and down 4, and I definitely don't see a vertex right there. I'm going to go left 6 and down 4. Still don't see a vertex there. So far, eliminating a lot of them. Back 6, down 4. Nope. And you're going to see it also doesn't work for this one. So this is where multiple choice kind of made our life really easy, and we're going to know that this is definitely going to be none of these. So now, a better question would be, what would that graph actually look like? Or how do I know exactly what it would look like? And here's what it would look like. So if we plotted that vertex, which we said that would be back about negative 6, and then down about negative 4, right, somewhere right there, it would be there. And then there's no other transformations happening to this function, so it would look just like a typical square root function. Just like that. Okay, so another one where we have to find a graph. So we can look at this, and again, we can use our inside rules and our outside rules, or the transformation rules. I can look inside there, and I can see that this is going to be a left 1, and I can see that this is going to be down 2. Oh, whoops, sorry, not down 2. It's going to be up 2. Now again, how can I do that? That's because I know my transformation rules, and I know that outside associates with up and down, and inside associates with left and right. And inside, I have to remember it's always the opposite of the sign. So I should expect my vertex to be there, so I'm going to look for something that went left 1 and down 2. So left 1, down 2, well, nope, not a. Left 1, no, this doesn't even go down 2, so that's not going to be it. Left 1, down 2, oh, god dang it, I'm sorry, I'm doing it again. It's not left 1 and down 2, it's left 1 and up 2. This graph was a little bit misleading, my apologies. So we're still going to see that that one doesn't work. And we're going to look at this one over here. And it goes left 1 and up 2. Nope, it's still not this one. This one's going to go left 1 and up 2. So almost there, but not quite. So not that one. And this one's going to go left 1 and then up 2. So that's good, right? So far, this looks like it's most likely to be our winner. Now, we do have to prove that it's not none of these. So maybe just find one more piece of evidence that could convince you that this would be right. Now, what would that evidence be? Well, notice we have a 3 out here. And the 3 is multiplying our function. So again, we want to know our transformation rules and know that that's going to stretch it upwards by 3. And when you look at all these parabolas, you notice that these look kind of normal, despite this one being flipped upside down. Then you come to this one's like skinny mini. It's super thin. It's stretched vertically, very much so. And so we have a 3 that's multiplying it, and we can know that that 3 is going to stretch it. So that could convince us because we do kind of see a stretch of 3. Now, how do we know exactly that it's 3? Well, that's because usually parabolas go from their vertex over 1, up 1, and back 1, up 1. And here we see it going over 1 and up to 6, right? So that would have been stretched up by, oh, well, no, sorry, it's not up 6. I think it's actually about up 5. So it went over 1 and up about 5. So it went from 2 to 5, which is up 3. So instead of just going up 1, it went up 3, meaning that 1 got stretched to a 3. So we could know that one is it. Okay, find the inverse of this. So this is pretty cut and dry. There's 2 steps to find the inverse. We're going to have step 1, which is switch x and y. So we want to come to this equation. First off, I don't see a y in there, so I'm going to go ahead and interchange f of x for y, because they basically mean the same thing. And f of x can mean y, for all intents and purposes. So 2x minus 4 divided by 3. Okay, so I want to switch x and y, so I go ahead and I write x is equal to 2y minus 4 divided by 3. Okay, so I switch x and y, and now step number 2, I need to resolve for y. And that's it. Once I resolve for y, I have found my inverse, right? And technically, finding the inverse is just switching x and y, but we just want to get it back into the y equals format. So we're going to come down here, and we have x is equal to 2y minus 4 divided by 3. I can multiply both sides by 3 to get rid of that division of 3. So those can cancel. And I'll have 3x is equal to 2y minus 4. I can now add 4 to both sides to get rid of this minus 4. And remember, 3x and 4, they do not add. Those are not the same terms. So we have 3x plus 4, which is equal to 2y. And then I can go ahead and get rid of the multiplication of 2 by dividing by 2. Remember, everything on this side has to get divided. And so that's going to give me y is equal to 3x plus 4 divided by 2. So I can look for that as my equation. So 3x plus 4 divided by 2. Now, here's the thing, I think where a lot of you guys went wrong. I can look for 3 over 2. Oh, I mean, that's actually, never mind. I thought they were going to simplify the 4 over 2, which might make it a little bit harder to see, meaning that you would have something like a minus 2 or a plus 2 somewhere. But we can actually just see that it would 3x plus 4, well, that's the same as 4 plus 3x divided by 2. Okay. All right, so another inverse problem. So we have to find the inverse of each function, and then we have to graph its inverse. So notice there's inverse equations written right here. And so we can actually first maybe just find the inverse and then see if it's appropriately graphed. So I'm going to look at this, and the first thing I'm going to do when I see this equation is I notice I can make this a little bit easier for me. I'm going to associate the negative to each 2. So that'd be negative 2x, and that would be negative 2. And then I notice they're both divided by 5, so I'm just going to divide them both by 5 and write it like that. Now, why does that make my life easier? Well, because now my fractions aren't separated, they're together. And it's a lot easier if I need to get rid of this denominator to just multiply by 5, rather than treat these like independent objects with independent fractions. And it actually turns out I do need to get rid of that because, remember, the inverse. Well, I'm not going to write it. I'm going to go back to the previous screen. The inverse, right, is switching x and y, and it's resolving for y. So we're going to go ahead. We're first going to switch x and y. So normally we have y is equal to negative 2x minus 2 divided by 5. And then we can go ahead and take our inverses. So we take the inverse, and we have x is equal to negative 2x minus 2 divided by 5. Oops, sorry. That is going to be a y. And then we want to go ahead and solve for y. So we're going to solve for y by multiplying by 5 on both sides. And that's going to give us 5x. Oops, sorry. Probably getting a little bit tired. 5x is equal to, those 5's are going to cancel, and so we'll have negative 2y minus 2. And now we can go ahead and, get rid of that 2. So we can add 2 on both sides. That's going to get rid of that 2. And those, they don't add together. That's just going to be 5x plus 2, which is equal to negative 2y. Okay, so I'm almost there. Still got to get y on its own. I want to go ahead and divide by a negative 2 to get rid of that negative 2. So my negative 2's will cancel, and now I have both 5x plus 2 divided by negative 2. And I think this was the one where your fractions kind of messed with you a little bit. So, yes, it is. So you look at this and you might not quite see something that looks like this, but the thing is, there's something that is equivalent to this in here, right? There's something that is equivalent to this in here. So if you don't at first see this in here, you want to think, is there another way to rewrite this? And it actually turns out there is. Because if we split up 5x over negative 2 and 2 over negative 2. Whoops, sorry. I don't know where that negative came from. If I split this up, right, I have a fraction, I can go ahead and split it up. I then see that this can be equal to 5x over 2, or negative 5x over 2, and 2 divided by 2 can then just become 1. And with that said, you can quickly kind of see what's going on. Okay, and that's my apologies. I actually just realized there was supposed to be that negative on the 2. And 2 divided by negative 2 would be negative 1. Now real quick, why did that happen? Well, because negative 2 is dividing both numbers, so I put a negative 2 under both. So then I can finally see that this is actually just right here. Right, that's my negative 5x, or negative 5 over 2x, and then that is my negative 1. Meaning that this would actually be my answer. And I think a lot of you guys picked none of these because you didn't see something that quite looked like that, but that could totally be our answer. Now, another way of doing this, so notice it says then graph the function in its inverse. So you can also start to make a table for this. and we have negative 2x minus 2 over 5. So I can pick any number I want to plug into there. I'll pick 1. And the thing is, it's not going to make a nice number, but it's going to make a number I can still kind of graph. So I can have negative 2 times 1 minus 2 divided by 5. That's going to be equal to negative 2 times negative 1. That would be negative 4. And over 5, negative 4 divided by 5. Well, that's as simple as it can get. So our coordinate would be over 1 and down 4/5. So we would go over 1 and down 4/5. So down just a little bit, down really not that much. So there should be some kind of line right about there. And you can look on that one, you can see that we don't quite see it. And likewise, you could come over here and you could look at this one, and you can actually see that we do kind of see that, right? It's right there. And likewise, when you look at this, right, we have a negative on our 2. And so that 2 is multiplying the x, which means that would indicate the slope of it. So when we have a negative 2 on that, we could expect a slope of negative 2 or negative 2/5. So there'd be a slope on this that is negative, and you can see this one does point down when this one is pointing up, and this one is pointing down, but we could know that that one's not it because it is pointing upwards. Okay, so you can plug in numbers, and you can also plug in another number if you want, and you can kind of just keep on going like that. And yeah, you could do that until you feel like you have enough confirmation to let you know that this is your correct graph. Now, probably the best way to do it was by just finding the actual inverse and confirming it like that. But you also could try to sketch a graph and make sure that it makes sense with what you see over here. All right, and then very last question we're going to go over, number 11. So on this one, there's a couple things that we can quickly look for with this. We see a minus 4 that's happening inside of our operation. With our transformation rules, that means that this is going to go left. Oops, sorry, not left. Remember, it's the opposite of what we expect. It's going to be going left. Why did I say that again? Because I'm erasing the word left. This is going to be going right 4. And likewise, this is going to be going down 3. Right? Remember, that's just because of my transformation rules. So I'm going to expect the center of that function, or the vertex of it, to be going right 4 and down 3. So I'm going to look at this. Did this one go right 4 and then down 3? No, it went right 3 and then down 4. So not quite that one. All right, so right 4 and down 3. Well, this one looks good, so this one could be it. And right 4 down 3, well, no, that one definitely couldn't be it. And then right 4 down 3, well, no, this one couldn't be it. So again, I have options of none of these or this one. Now, how could I further confirm that this is my function? Well, another thing you can look at is the negative, right? There's a negative 3 on there, which tells you that this thing should be facing down. And it does face down, which is good, right? So that means this looks even more like the correct answer. Now, it also has a multiplier of 3 on it, so we could also expect a kind of stretch, a kind of stretch on this. And we do see a stretch on it, because normally this function would look something kind of like this, right? It would be more like a perpendicular V that goes kind of like this. But we don't see it doing that. We see it actually being pulled further up and down, which means there's a stretch going on with it. Okay, so that's how we can know that that's going to be the correct answer. All right, I hope this helped. If there's parts of the video you like or don't like, definitely let me know. I love getting better for you guys. So I'll talk to you guys later. Bye.